So let's continue. You see, this vector position R is equal x1 e1 plus x2 e2 plus x3 e3. But you see, this is x1, this is x2, and this is x3. See? So these are rectangular coordinates. Then I substitute here, so I will have x1 is rho cosine theta u1 plus x2 is rho sine theta e2. That's the same cylindrical and rectangular coordinates. So this will be z e3. Remember, ours this e I dot ej delta ij. Okay? What this means? Orthogonal base vectors. See? Now, I can now, okay, from previous videos, look at how easy, okay, partial of R with respect to rho. Look, E1, E2, E3, they are constant, okay? You can move point to point. E1, E2, E3, they don't change. They're the same. But if you move to another point, you see here, actually there will be another rho, another theta, okay, and another z. So partial R with respect to rho, look at here. Another point that I did emphasized is this: rho, theta, and z, they are independent, okay? Like x, y, and z, they are independent, okay? In general. Now, if I derive this right-hand side with respect to rho, then I'll get. Now, this is a partial derivative, okay? Partial derivative, don't forget, I maintain theta and z constant. That's a partial derivative. So this will be cosine theta e1, now plus sine of theta e2. Now here there is no rho. You see that? I'm deriving with respect to rho plus 0 e3. See? That is 0. But I take derivative, so the whole term here will be 0. 0 vector. Now, look at that, how interesting. Now, this over here, I will define as A sub rho, okay? You can see clearly that A sub rho is equal partial derivative with the position vector rho. Now, let's derive R with respect to theta. Attention now, here rho and z remain constant. Then I'll look at here and I see this will be minus rho sine of theta u1. Derivative of sine theta plus rho cosine theta e2 plus 0, you see? 0 vector. Okay? So the whole equation is a vector. This I can write like this. Rho multiplies minus sine theta u1 plus cosine theta e2. Okay? That's important. You see, when I derive the position vector with respect to one of the coordinates, this will be tangent to whole direction. This will be tangent to theta direction. Don't forget that. I already discussed this previously. So I raise here. That's a very, very important. Okay? Then I say that I could say that, look at that, I have my axis, okay? This will be x1, x2, x3, rectangular coordinate. And now, there's a point P, okay, point P over here. This P, attention now, can be expressed by x1, x2, x3, or P, rho, theta, and z. You see, P is invariant, it's a point. I can express like that, okay? Now, I will draw here. This is my vector position. This over here on the floor, okay? This is a point Q, okay? Then here, look how interesting it is. This is rho, this is E, rho. You see, now, this is rho. Now, I'll have my angle theta, okay? Then, you see, partial derivative of this, I can write this as A theta, see? There's a tangent vector. My goodness, look at that, how it's simple. I'll write here A rho. I'll tell you why. This is A theta, which is tangent to this curve. Okay, this is a curve. Okay, and this is A rho. Now how I can find some properties of these two vectors. So this is a base vectors in cylindrical coordinate. The base vector R. Look at that. So this is A rho, A theta. Now I'll say, look, no problem. I'll write A Z. But AZ is perpendicular. This is, I'll put here, AZ. which is the same as V3. See? In the traditional notation, this is a unit vector, K. Okay? So, now let's see some interesting properties of this base vector. You see, look at here, look, base vectors in cylindrical coordinates. Look, let's take the dot product, a row dot a row. Okay? Now, I just substitute. What is a row? You see, it will be cosine theta E1 plus sine theta E2 dot, I'll repeat this, cosine theta E1 plus sine theta E2. It's easy, easy. Remember that. Remember, EI dot EJ is delta IJ. Remember all of this, because this belongs to the rectangular coordinate.